Hello, everyone. My name is Anup. I'm a technical consulting engineer and I work with Intel Developer Products Division. Well, today I'm going to talk about a new feature which we have as a part of Intel System Studio 2015, which is using Intel processor graphics for general purpose computing. Doesn't that sound cool? Because until now, Intel processor graphics was actually used extensively for 3D rendering as well as for video processing. Right now, with this new feature which we offer as a part of our 15.0 compiler, well, you can use our programming model to go ahead and offload highly computation intensive as well as highly data parallel code in your application onto processor graphics. The key idea here is that when you use both the CPU cores as well as the GPU cores in tandem, that's when you can get the best performance from the processor. Now, obviously, you can ask me why processor graphics offload at the first place? Well, my answer is why not processor graphics? Because in the case of processor graphics, with every generation of processor, starting from third generation Intel Core, moving on to fourth, and even further, the emphasis of compute power on Intel processor graphics is increasing generation by generation. Let it be the significant processor graphics area which it occupies on the silicon, or let it be in terms of the computation power which is expressed in parallelism. Now, coming to the parallelism. So what is so explicit about that? Well, this processor graphics hardware has a certain number of execution units, and each execution unit has a certain number of hardware threads, and each hardware thread executes in a SIMD mode. That's very important. Now, for instance, just to give you some numbers, let's consider the fourth generation Intel Core processor with a processor graphics SKU, which is Intel Iris Pro Graphics 5200. In that specific SKU, you have 40 execution units, each execution unit hosting 7 hardware threads, which means in total you have 280 hardware threads, and each hardware thread executing in SIMD mode. So you can imagine the amount of compute power which is hidden in that small piece of silicon. Why not use it for general purpose computing? So that's exactly what we have done, unlock this piece of compute power through the new feature in our compiler in 15.0. So obvious question is, well, I understand the compute power right now, so how do I go ahead and port my existing application to processor graphics? Well, we have made that part easier for developers. And the way we have made it easier is by using or expressing the parallelism on the processor graphics side by using Intel Silk Plus programming model. Well, it is the very same programming model which we are using on the host side to express both parallelism as well as vectorization. So that makes it much more easier and productive for developers to go ahead and port their program onto processor graphics for execution. Well, that's the best part for folks who are already using Intel Silk Plus programming model. Now, coming to two big advantages of Intel processor graphics. Unlike any discrete graphics cards, which is also good for general purpose computing, the main problem which you face in the discrete graphics cards is that any kernel which needs to execute on the discrete graphics card, you need to make sure the data is also explicitly copied from the system RAM to the card memory so that it's ready for execution. Well, the advantage which you have with Intel processor graphics is that the GPU cores can directly access the system RAM, which means you are avoiding that memory or the data transfer penalty here. And second biggest advantage is that every hardware thread has an exclusive or mutually exclusive 4 KB general register file, and that's the fastest memory which a GPU core has access to. So as long as you can tile your data such that the hardware threads can access just the general register file, you are running your code to the best possible performance, and you are making sure that the memory latency is the minimal. Well, regarding the offload models which we have to support, currently we have two offload models. One is called as the synchronous offload model, which is more of a pragma based approach to annotate your section of code which is actually highly data parallel and making sure that that part gets offloaded to processor graphics. Well, the other approach which we have is the asynchronous offload model, which is more of an API based approach rather than the Pragma based approach. Well, if you guys are really interested in knowing the very technical details on how the offload works and how do you annotate your source code so that the compiler takes the necessary actions, please feel free to go and visit the URL which is down there, and you could see the technical details in the webinar, which is titled Maximize Graphics Processor Power for General Purpose Computing. So there you would actually find more details on how the offload is done, and also the details about the hardware as well as the operating system which you need to have where we support this feature. Just to highlight on a higher level, we support Windows 32 and 64-bit targets, and starting from Windows 7. And regarding the Linux 64-bit, we support two different flavors of Linux. It's Ubuntu 12.04 and SLES11 SP3. Again, please look into the slides of the webinar for more details on which specific Linux kernel numbers we do have this support on. Hopefully I've set the pitch right for you guys, and you look forward to see you for the future webinars on this topic too. Thanks for watching.